Dear friends, in this video, I propose to address two important rules that are very useful in application as well as research. In the context of behavior of the data and the shape of the distribution, we use two rules, the empirical rule and Chebyshev's rule. Empirical rule means it is based on data, data-driven rule. Based on data, if you have empirical evidence that a distribution is a bell curve, for example, then what we say is the following. If the distribution is a bell curve, approximately 68% of the data points will be within one standard deviation departure from the mean or within mu plus or minus 1 sigma. So this part is 68%. This is important. So by the property of symmetry, this will be 16%, this will be 16%, and the entire range is 68 percentage points. In other words, only if it is a bell curve, this rule holds true that, let's say you construct a histogram and approximately you are convinced it looks like a bell curve. Then you can apply this rule. That's the beauty. Now, if you extend this to, let's say, to within plus minus 2 sigma. In other words, 95% approximately, you should never say it is exactly 95%, it won't be. 95% of the data points, if the original distribution looks like a bell, 95% of the data points will be within mu plus or minus 2 sigma or a departure from the mean by mu plus or minus 2 sigma. This is the second rule. Now, in the empirical rule, supposing the original distribution is a bell curve, it says 99% of the data points approximately will be within a range of mu plus or minus 3 sigma. In other words, the departure from the mean on either side, if you include, it will be 99.7% of the data points. In other words, the probability that a particular data point will fall in the range mu minus 3 sigma to mu plus 3 sigma will be 99.7%. This is very important. So to recapitulate, if you take mu plus or minus sigma in a distribution that looks like a bell, it will be 68% of the data points approximately in that range. And if you take 2 sigma departure from the mean, it will be 95% of the time the data points will be in that range. And if you take 3 sigma departure from the mean, you will have approximately 99.7% of the data falling in that range. Supposing it is not a bell curve, what do? Only in the case of bell curve, it holds true. Now, there is another interesting theorem, which we call it as a rule, Chebyshev's theorem. We call it as Chebyshev Rule. The mathematician discovered that it is mathematically proven theorem. It is not empirical. It is always true. So regardless of the shape of the distribution, at least 1 minus 1 upon k squared values of the data set will be within k standard deviation departure from the mean, or it will be within plus minus k sigma range from the mean. provided k is greater than 1. So if you multiply this by 100%, it will be expressed as a percentage. So let us take an example. If k is equal to 2, you are saying at least 1 minus 1 upon 4, which will be 75% when you multiply by 100, 75% of the values or the data points will be within mu plus or minus 2 sigma. This is the beauty of Chebyshev's rule. And if you take, for example, k is equal to 3, 1 minus 1 upon 9, which will be 8 by 9, approximately 89 to 90% of the data points will be within, it is at least, not approximately, sorry, at least 89 to 90% of the data points will be within mu plus or minus 3 sigma. But I have taken only an example here when k is 2, at least 75%. It doesn't say approximately 75%, at least 75%. It could even be more. And very important thing for all of us to remember and ponder is Chebyshev's theorem is always true, regardless of the distribution shape, whereas the empirical rule is applicable only when the distribution is a bell curve. There is no guarantee all problems will have a shape of a bell curve. Thank you very much. We will see you soon in the next video. Thanks a lot.